Electronic structure investigations of 4-Aminophthal Hydrazide. Abstract combined experimental and theoretical studies were conducted on the molecular structure and vibrational spectra of 4-Aminophthal Hydrazide, APH. The FT-IR and FT-Raman spectra of APH were recorded in the hard phase. The molecular geometry and vibrational frequencies of APH in the ground state have been calculated by using the ab initio HF, Hartree-Fock, and density functional methods, B3LYP, invoking 6-311 plus G, dp, basis set. The optimized geometric bond lengths and bond angles obtained by the HF method show the best agreement with the experimental values. Evaluation of the experimental fundamental vibrational frequencies of APH with designed results by HF and density functional methods indicate that B3LYP is superior to the scaled Hartree-Fock move towards molecular vibrational problems. The difference between the observed and scaled wave number values of most of the fundamentals is very small. A detailed interpretation of the FT-IR and FT-Raman, Nmr spectra of APH was also reported. UVvis spectrum of the compound was recorded and the electronic property, such as HOMO and LUMO energies, were performed by time-dependent density functional theory, TD-DFT, approach. Ultimately the results of the calculation were functional to simulated infrared and Raman spectra of the title compound which show good agreement with observed spectra. And the temperature dependence of the thermodynamic properties of constant pressure, Cp, entropy, S, and enthalpy change, H0.T, for APH were also determined. Keywords, FT-IR, FT-Raman, HOMO LUMO, NMR, UV, APH. 2. Introduction. Hydrazides and hydrazones, the acylated derivatives one of hydrazine. Besides being useful for many biological properties, hydrazides are important starting material for a wide range of derivatives utilizable in pharmaceutical products and as surfactants. The hydrazones derivatives are used as fungicides, and in the treatment of diseases such as tuberculosis, leprosy, and mental disorders. Biological assessment of fatty hydrazide and the derivatives has been the focus of earlier investigative studies 2,3. The fatty hydrazides are further derivatives to obtain new antibacterial and antifungal agents. Acyl hydrazones, as an example of Schiff bases, and their metal complexes have widely studied due to their versatile applications in the fields of analytical and medicinal chemistry and biotechnology. 4-6. P-hydroxybenzohydrazide moiety and its analogues seem to be suitable parent compounds upon which a variety of biological activities were reported such as anti-tumor, anti-anginal, antitubercular, anti-hypertensive and antibacterial. 7. Hydrazides have recently become attractive to theoreticians as well as experimentalists due to the biological significance, particularly in medicinal and enzyme chemistry. A lot of substituted hydrazides are employed in the treatment of psychotic and psychoneurotic conditions. Carboxylic acid hydrazides are known to exhibit strong antibacterial activities that are enhanced by complexation with metal ions. The vibrational spectral studies of hydrazone was analyzed by DIRT ETAL8. The FT-IR and FT-Raman spectra of 4-Aminophthal Hydrazide, APH, and carried out normal coordinate calculations using the classical method developed by Wilson to support the vibrational analysis. 9. To our knowledge, the literature survey also reveals that to the best of our knowledge no theoretical calculations or detailed vibrational infrared and Raman analysis have been performed on APH molecules so far. A systematic study on the vibrational spectra and structure will aid in understanding the vibrational modes of this tidal molecule. So, in this work, the vibrational wave numbers, geometrical parameters, modes of vibrations, minimum energy, 1h, and 1,3C NMR chemical shifts are calculated with GIAO approach by applying B3LYP method, and electrostatic potential also provide information about electronic effects of APH molecule was investigated by using ab initio HF and B3LYP calculations with 6-311 plus G, dp, basis set. Specific scale factors were also used and employed in the predicted frequencies. The electronic dipole moment, and the first hyperpolarizability, SS, value of the investigate molecule computed show that the APH molecule might have microscopic nonlinear optical, NLO, behavior with non-zero values. The UV spectroscopic studies along with frontier molecular orbital, FMOs, and their energy gaps were analysis. The temperature dependence of the thermodynamic functions and their correlations were performed. 3 experimental techniques. Synthesis procedure of 4-Aminophthal Hydrazide. This was performed by adding hydrazine hydrate 10 grams in 20 ml water to a suspension of 4-nitrophthalimide, 38.4 G, in 250 ml water and refluxing for 1 hour. This solution was acidified with acetic acid and cooled, and the pale yellow crystalline product was collected with suction. Purification was accomplished with a solution in 3 liters boiling 50% acetic acid, rapid filtration, followed by cooling and collection of pale yellow product. The melting point of 4-Aminophthal Hydrazide 299-300 OC. The calculated, found, percent for C8H7N3O2, C, 54.24, 53.24, H, 3.98, 3.95, N, 23.72, 22.71, and O, 18.06, 17.04. The room temperature Fourier transform infrared, FT-IR, spectrum of the title molecule was recorded in the range of 4000 to 400 cm1 at a resolution of plus or minus cm1 using a Bruker IF 66V FT-IR spectrophotometer equipped with a cooled MCT detector. Boxcar apodization was used for the 250 averaged interferograms collected for both the samples and the background. The FT-Raman spectrum was recorded on a computer-interfaced Bruker IFS model interferometer, equipped with Fra 106 FT-Raman accessory in the 3500 to 50 cm1 Stokes region, using the 1064 nm line of ND, YAG laser for excitation operating at 200 MW power. The reported wave numbers are supposed to be accurate within plus or minus 1 cm1. The UV visible absorption spectra of APH are examined in the range 200 to 600 nm using Shimadzu UV 1650 PC, UVvis recording spectrometer. The UV pattern is taken from 10 to 5 molar solution of APH, solved in ethanol. Computational details. Density functional theory calculations were carried out for APH, Hartree-Fock, HF, and DFT calculations using the Gaussian 09W program package 10. Initial geometry generated from the standard geometrical parameters was minimized without any constraint on the potential energy surface at the Hartree-Fock level, adopting the standard 6-311 plus G, dp, basis set. This geometry was then re-optimized again at DFT level employing the B3LYP keyword, which invokes Beck's 3-parameter hybrid method 11 using the correlation function of Lie etal12, implemented with the same basis set for a better description of the bonding properties of the amino group. All the parameters were authorized to relax and all the calculations converge to an optimized geometry which corresponds to a true minimum, as exposed by the B short of imaginary values in the wave number calculations. The multiple scaling of the force constants were performed according to SQM procedure 13 using selective scaling in the natural internal coordinate representation 14. Transformation of force field, the subsequent normal coordinate analysis including the least square refinement of the scale factors and calculation of the total energy distribution, TED, was done on a PC with the Malvibe program, version v7.0 G77, written by Sundias 15,16. The methodical assessment of the results from DFT theory with the results of the experiment has shown that the method using B3LYP well designed is the most hopeful in providing correct vibrational wave numbers. The calculated geometrical parameters were compared with the X-ray diffraction result 17. Normal coordinate analyses were carried out for the title compound to provide a complete assignment of fundamental frequencies. For this purpose, the full set of 77 standard internal coordinates, containing 23 redundancies, for APH was defined as given in Table 1. From these, a non-redundant set of local symmetry coordinates were constructed by suitable linear combinations of internal coordinates following the recommendations of Foguera CET. AL14 is summarized in Table 2. The theoretically calculated force fields were transformed into this set of vibrational coordinates and used in all subsequent calculations. Prediction of Raman intensities. The Raman activities, SI, calculated with the Gaussian 09W program were subsequently converted to relative Raman intensities, 2, using the following relationship derived from the basic theory of Raman scattering 18. Where point 0 is the exciting frequency in Cm1, I the vibrational wave number of the ith normal mode, h, c, and k are the fundamental constants and f is a rightfully chosen ordinary normalization factor for all the peak intensities. 6 Results and discussion. 4.1 Molecular geometry. The optimized molecular structure of APH along with the numbering of atoms is shown in Fig. 1. The optimized structure parameters of APH obtained by DFT B3LYP/6-311 plus G, dP, and HF/6-311 plus G, dP, levels are listed in Table 3. From the structural data given in Table 3, it is observed that the various bond lengths are found to be almost the same at HF/6-311 plus G, dP, level of theory, in general slightly overestimates bond lengths but it yields bond angles in excellent agreement with the HF method. The intended geometric parameters can be worn as a foundation to work out the other parameters for the compound. The optimized molecular configuration of APH reveals that the N-heterocyclic rings of the amino group are in planar. Inclusion of CH group and NH atoms known for its strong electron withdrawing nature, in heterocyclic position, is expected to increase a contribution of the resonance structure, in which the electronic charge is concentrated at this site. This is the reason for the shortening of bond lengths N11H12 equals 0.994A0 and N11H13 equals 0.995A0 obtained by the HF method. The same bond lengths calculated by the DFT method is found to be 1.009A0 and 1.010A0. The carbon atoms are bonded to the hydrogen atoms with the S bond in the heterocyclic ring and the substitution of hydrogen atoms for hydrogen reduces the electron density at the ring carbon atom. In APH, the NH bond lengths vary from 0.997A0 to 0.999 by the HF method and from 1.013 to 1.014 B3LYP methods. The ring carbon atoms in substituted heterocyclic exert a larger attraction on the valence electron cloud of the hydrogen atom resulting in an increase in the CH force constants and a decrease in the corresponding bond length. It is evident from the CC bond lengths ranging from 1.375A0 to 1.489A0 by HF method and from 1.385 to 1.485 by B3LYP method in the heterocyclic rings of APH, whereas the CH bond lengths in APH vary from 1.073A0 to 1.076A0 and from 1.084 to 1.086A0 by HF and B3LYP methods, respectively. The heterocyclic rings appear to be a little distorted because of the NH2 group substitution as seen from the bond angles C3, C4, C5 which are calculated as 118.96 degree and 118.76 degree respectively, by HF and B3LYP methods and are smaller than the typical hexagonal angle of 120 degree. The comparative graphs of bond lengths, bond angles, and dihedral angles of APH for 3 sets are presented in Figs 2 to 4 respectively. From the theoretical values, it is found that most of the optimized bond lengths are slightly larger than the experimental values, due to that the theoretical calculations belong to isolated molecules in the solid phase and the experimental results belong to molecules in solid state. Comparing bond angles and lengths of B3LYP with those of HF, as a whole the formers are bigger than later and the B3LYP calculated values correlate well compared with the experimental data. 4.2 First hyperpolarizability. The potential application of the title compound in the field of nonlinear optics demands the investigation of its structural and bonding features contribution to the hyperpolarizability enhancement, by analyzing the vibrational modes using IR and Raman spectroscopy. Many organic molecules, containing conjugated p electrons are characterized by large values of molecular first hyperpolarizabilities, which were analyzes through vibration spectroscopy 19. In most of the cases, even in the absence of inversion symmetry, the strongest band in the IR spectrum is weak in the Raman spectrum and vice versa. But the intramolecular charge from the donor to acceptor group through a p-bond conjugated path can induce large variations of both the molecular dipole moment and the molecular polarizability, manufacture of IR and Raman activity strong at the similar time. The experimental spectroscopic behavior described above is well accounted for calculations in p-conjugated systems that predict exceptionally infrared intensities for the same normal modes. The primary hyperpolarizability, SS, of this novel molecular system is calculated using the ab initio quantum mechanical method, based on the finite field approach. In the presence of an applied electric field, the energy of a system is a function of the electric field. The primary hyperpolarizability is a third-rank tensor that can be described by a 3x3x3 matrix. The 27 mechanism of the 3D matrix can be synopsis to 10 mechanisms due to the Kleinman symmetry 20. The mechanism of SS is exact as the coefficients in the Taylor series swelling of the energy in the external electric field. When the electrical field is feeble and all the same, this growth becomes where E0 is the energy of the unperturbed molecule, phi is the field at the origin, and IJERT, and IJERT are the components of dipole moment, polarizability, the first hyperpolarizabilities, and second hyperpolarizabilities, respectively. The calculated total dipole moment, and mean first hyperpolarizability, SS, of APH are 1.1437 by an 8.3541 x 1030 ISU, respectively, which is comparable with the reported values of similar derivatives. The large value of hyperpolarizabilities, SS, which is a measure of the nonlinear optical activity of the molecular system, is associated with the intermolecular charge transfer, resulting from the electron cloud movement through p-conjugated framework from an electron donor to electron acceptor groups. The physical properties of these conjugated molecules are governed by the high degree of electronic charge delocalization along the charge transfer axis and by the low band gaps. So we conclude that the title compound is an attractive object for future studies of nonlinear optical properties. 4.3 Nmr Spectral Analysis. The isotropic chemical shifts are frequently used as an aid in the identification of reactive organic as well as ionic species. It is documented that correct predictions of molecular geometries are necessary for reliable calculations of magnetic properties. Therefore, the full geometry optimization of APH was performed by using the B3LYP/6-311 plus G, DP, method. Then, gauge including atomic orbital, GIAO, 1H and 13C chemical shift calculations of the compound have been made by the same method. Application of the GIAO-21 approach to molecular systems was significantly improved by an efficient application of the method to the ab initio SCF calculations, using techniques borrowed from analytic derivative methodologies. GIAO procedure is somewhat superior since it exhibits a faster convergence of the calculated properties upon extension of the basis set used. Taking into account the computational cost and the effectiveness of calculation, the GIAO method seems to be preferable from many aspects at the present state of this subject. On the other hand, the density functional methodologies offer an effective alternative to the conventional correlated methods, due to their significantly lower computational cost. The molecular structure of APH is optimized by the B3LYP method with 6-311 plus G, DP. Then, gauge including atomic orbital, GIAO, 13C and 1H chemical shift calculation of title compound is made by using the B3LYP method. The 1H and 13C chemical shifts were measured in a less polar, CdCl3, solvent. The result in Table 4 shows that the range 13C NMR chemical shift of the typical organic molecule usually is greater than 100 ppm 22,23. The accuracy ensures reliable interpretation of spectroscopic parameters. It is true from the above literature value. In our present study, the title molecule APH also falls with the above literature data except with the carbon atoms, C4. In the present paper, the signal observed at 190.30 ppm in the 13C Nmr spectrum is assigned to C10 carbon atom correlates with theoretically predicted value at 187.473 ppm. The signals for aromatic carbons were observed at 127.70 184.70 ppm in the 13C Nmr spectrum for the title molecule, since those carbon atoms which belong to APH also exactly correlate with theoretically predicted value at 114.474 186.714 ppm. The signals of the aromatic proton were observed at 21.90 22.03 ppm. The calculated 24.950 to 25.037 ppm proton NMR chemical shifts show moderate agreement with the experimental values except with aliphatic proton H16, H17. The H atom is the smallest of all atoms and mostly localized on the periphery of molecules. Therefore their chemical shifts would be more susceptible to intermolecular interactions in the aqueous solution as compared to that for other heavier atoms. Another important aspect is that hydrogen attached or nearby electron withdrawing atom or group can decrease the shielding and moves the resonance of the attached proton towards a higher frequency. By contrast, electron donating atom or group increases the shielding and moves the resonance on the way to a lower frequency. In this study, the chemical shifts obtained and calculated for the hydrogen atoms of amino groups are high. All values are 24 due to the shielding effect. It is true from above literature data in our present study the amino protons at N11 appears as singlet with two protons integral at 27.40 to 27.41 ppm shows good agreement with computed chemical shift, 30.606 to 30.418, values are shown in Table 4. The relationship between the experimental chemical shift and computed GIAO/B3LYP/6-311 plus G, dP, levels for 13CA and D1H are shown in Fig. 5. 4.4 HOMO-LUMO analysis. Many organic molecules that contain conjugated p electrons are characterized by hyperpolarizabilities and were analyzed using vibrational spectroscopy 23. In most cases, even in the absence of inversion symmetry, the weakest bands in the Raman spectrum are strongest in the IR spectrum and vice versa. But the intramolecular charge transfer from the donor to the acceptor group through a single double bond conjugated path can induce large variations of both the molecular dipole moment and the molecular polarizability, making IR and Raman activity strong at the similar time. It is also experimental in the title compound. The bands in the FT-IR spectrum have their counterpart in Raman show that the relative intensities in IR and Raman spectra are similar, resulting from the electron cloud movement through p-conjugated casing work from an electron donor to electron acceptor groups. The highest engaged molecular orbital, HOMO, and lowest unlived in molecular orbital, LUMO, are very important parameters for quantum chemistry. We can conclude the way the molecule interacts with previous species, hence, they are called the frontier orbitals. HOMO, which can be thought the outermost orbital containing electrons, tends to give these electrons such as an electron donor. On the other hand, LUMO can be thought the innermost orbital containing free places to accept electrons 25. Outstanding to the interaction between HOMO and LUMO orbital of a structure, conversion state transition of p** type is observed about the molecular orbital theory. The calculated self-consistent field, SCF, energy of APH is -623.9537 AU. Therefore, while the energy of the HOMO is in a straight line related to the ionization potential, LUMO energy is directly linked to the electron affinity. The energy difference between HOMO and LUMO orbitals is called an energy gap that is important stability for structures. Also, the pictorial scheme of a few moles of APH is shown in Fig. 6. HOMO is localized on the central ring and has partially contribution from the substitution groups such as oxygen and amino group. LUMO is quite localized on the central ring and has a strong contribution from the substituted electronegative oxygen and amino group. The energy gap between HOMO and LUMO is 0.1058 AU, which shows that charge transfer may be taking place from the ring to oxygen atom. As seen in Fig 6, HOMO 1 is very similar to HOMO, rotated by 90. HOMO 3 is mainly localized on ring carbon atom, whereas LUMO plus 3 is localized on ring carbon atoms and an oxygen atom. HOMO-LUMO energy gap and related molecular properties of 4-Aminophthal Hydrazide from Table 5. Conclusion. In this present investigation, molecular structure, vibrational frequencies, HOMO, LUMO, and polarizability analysis of APH have been studied using ab initio HF and DFT, B3LYP/6-311 plus G, DP, calculation. The Nmr, 1H and 13C, spectral studies were carried out for the first time. Any discrepancy noted between the observed and calculated frequencies may be because the calculations have been done on a single molecule in the solid state, contrary to the experimental values recorded in the presence of intermolecular interactions. Based on the agreement between the calculated and observed results, assignments of fundamental vibrational modes of APH were examined and some assignments are proposed. This study demonstrates that scaled DFT/B3LYP calculations are a powerful approach for understanding the vibrational spectra of the medium-sized organic compound. Temperature dependence of the thermodynamic properties, heat capacity at constant pressure, Cp, entropy, S, and enthalpy change, H0.T, for APH were also determined by B3LYP/6311 plus G, DP, method. The UV spectrum was calculated in an ethanol solution. The theoretically constructed FT-IR and FT-Raman spectrum shows a good correlation with experimentally observed FT-IR and FT-Raman spectrum. The internal coordinates used here are defined in Table 1. Table 3. Optimized geometrical parameters of 4-Aminophthal Hydrazide obtained by HF/6-311 plus G, DP and B3LYP/6-311G plus, D, P, density functional theory calculations. Bond length.